All right, I put up on the, oh, I thought I put it up. I don't see it. My mistake. Again, on Blackboard, under the Atmel manuals, tutorials, and all that stuff, the 169P is up there. I also, I loaded up the Atmega 32, which is what the book uses, so just that you'll have it. Okay, so just, I don't know why I don't see it up here, but it may take a little bit to get that thing going. All right. All right. All right, I think we left off, we were doing some examples. All right, yeah, so again, you have the data memory is comprised of three things. Three things, okay? Three. Miles, go ahead.
General purpose register.
GPRs,
Special function.
SFRs, and SFRs, and IO are all sitting in that spot, and then your general purpose SRAM. Okay, so that's data memory. Okay, that's data memory. All right, and you can write to any one of these. All right. He asked me the other day, he's there, Doc, he's there, you wrote a 9.5 to the wrong place or something. When you start writing in here, sometimes you can write to it. Sometimes certain bits in these registers cannot be written to. They are protected. Okay? And we're going to show you what happens when you start playing around in here. You got to be real careful. Here is where you want to write to, and here is where you want to write to. Okay? And we're going to write, well, you just got to be careful in here. All right? There's two kind of addresses that go on inside of here. There is the physical address. In his case, it goes from 0020 up to 5F. All right? And if you'll notice over here, there's something called the IO address. All right? The IO address. So each one of these guys in here physically has two addresses. Okay? There's one, which is the data address space. And then there's what's called the IO address. And we'll get to this down the road a little bit, okay? All right, so what we were doing is we just did some loads the other day. You did some loads today. And simply, and storing to data space, you just give it an address and from a register, okay? So if I just took register 15, contents of register 15, wrote it to memory location 060. It just takes that guy and stores it up there. Okay. Writing a 55 into a memory location. Again, just put it into a general purpose register, and then take that register contents and write it to a physical memory address. Yeah.
Can you use the LDS also? Can you use either one?
LDS.
The LDS one.
What's LDS do? Load data space.
Could you use that also?
What, to do instead of STS? What's the LD for? LD is loading to what? Where am I loading it to? Look at the op code. Where am I you're asking, can I use LD to write to data space? Is that what you're asking? LD is to write to where? LD deals with what? Louder! Registers. All right? Then ST is to store to SRAM. Okay? No, really, it's a good question. It's, yeah. All right, write a program to copies, so we all right? So all you're doing is just loading in a hex value in R20 and then just write it to there. Okay? Here what we're going to do is add the contents of location 90 to 95 and store the result in 313. So you just load in 90 gets loaded into here, 95 gets loaded into, and then you just simply do an add, and then we do a simple write, okay? So here I'm writing to, now again, this is processor specific, so you have to know what processor you're doing and where you're writing it to. And we'll get to, there was a couple, here, this was, if I just take this guy, we're going to load to R20. It copies the contents of R2, because where is that memory location sitting at? Where is this guy sitting at? Right here. That 2. It's in data memory, but where is it? It's right there. It's taking the contents of that general purpose register, which is sitting in R2. See, this memory location right here is R0. That memory location is R1. And then if I load a 2, 0002, which is that defaults to, it's going to copy the contents of register R2 into R20. Okay? All right, store 53 into, now this is called the stack pointer high. And 53, all right, at the address for the SRAM is 55F, so we're going to take 53, load it into R20, and then store that into 5F, all right, which is the status register, which we will talk about today, all right. So again, be careful picking your poison. So here I've got from the 169 manual that you asked the other day, right? This is for the 169P. This is right out of figure 7.2 from the manual, all right? Your data memory, you've got your, so this is data comprised of, as Miles said so eloquently, 32 registers, IOs and SFRs, and then my internal RAM. So again, when you're writing stuff here to internal RAM, you must start at location 0100 and then work your way down to 4FF. Okay, that gives me to 1K. Go ahead.
Using the command STS, do you have to load, or do you have to write a register to the data memory, or can you just write a value?
You want to write a value to?
Because in this example you just did with the data address space in the last slide, you were just writing like a register.
Right here? This one?
Yeah.
Yeah.
Can you just use a value and write it to that space?
To STS?
Yeah.
Yeah, we'll get to it.
Okay.
Yeah. All right. Now again, for the 169P, this gives you all of the, this is all of the, again, you have 2 types of addresses are going on here. The IO address starts at 00, but the physical memory address starts at 020 here, all right, which is denoted right here. That number there is that physical memory location there, okay? And you'll see all these, names that are in here. TWBRs, ADCL, ADCH, this stuff down here, PIND, this is the to control port D, all right, as an input. The data direction register for port D is here. This is how you select port D. The actual physical, you have 2 ports on your butterfly board, all right? You got port B to play with and port D to play with. You can take any one of those 8 pins on port B or any of those pins on port D and selectively make them inputs and outputs, okay? So they can accept a voltage in or they can put a voltage out. We'll get to in these slides, I'll be showing you how to write to the LEDs, all right, how to write the LEDs. The other day when you got your little boards, you guys were basically writing to the speaker, right? You were physically writing to the speaker. All right, we'll get to that code in a little bit. All right, so all this stuff in here. Here you've got this is a timer counter. We've got, you don't have access to port A and port. There's port A. I think it goes A through F. You only have direct access to ports B and D on your butterfly board. On the other boards, you have access to them. And if you notice, just on that slide there, that's the 5E is duplicated there. The SRAM, the status register, is physically at 5F. Okay, so just note that on your thing there. All right. So the direct addressing, LDS, RD, and then you just give it address. All right. So again, we went through this the other day. Here's my opcode. Same thing over here. My opcodes are set up here, and then we have data, and then we have the physical 16-bit address that goes here. So the 313 would be 0313 would go into right in here. Okay. Let's see. And yeah, I actually took down, I went into the LSS file for this guy, and here you can see it. What we were doing is the register R19, and now when I have 19 followed by a D, sometimes I will put a subscript here and put a 10. That means base 10, where D is for decimal. If it's followed by an H, it would be hex. Followed by a B, it would be binary. So the 19 decimal comes out to be 10011. All right. So you lop off that guy. I'm left with the 3, and the 3 is right there. Okay. So that's just how to read the opcode for it. All right. Sir, you had a question about this the other day, right? This one? All right, so let's load this one up. And we're going to run it on a couple different processors, okay? So just grab that code. If you notice, if you download the slides from like Monday to Wednesday and you have them on your flash drive, they change every day. I am on the bus from Ambler to here writing code, changing slides. When I'm sitting at my home on Tuesday, Thursdays, I'm writing code, changing slides. They change all the time, all right? So just be aware of that, all right? I'm constantly modifying this stuff. All right, so let's hit the assembler. And, all right, you know what? Let's run this first on the 2560. All right, so just hit your 2560. Now, this has lots of SRAM. The 2560 has a lot. And we'll show you the memory space for it in a second. Let me go here. I think I loaded up. I changed these slides a little bit. I think somewhere back here. Ah, here we go. Right here. All right, when we're talking about the SRAM data, on the ATmega, you've got, it goes up to 4FF, which gives me 1K. Okay, it's 1K by 8 bits, all right? If you go to the Mega 2560, all right, you've got these 32 registers. I've got 64 I.O. registers sitting in there, 416 internal I.O. registers, and the internal SRAM starts at 0200, okay? So when you're on a 2560 and you want to start writing data, you start here, or it has to be here or somewhere below it. Now don't worry about down to here. We don't have the external SRAM on it, so we're going to write from 0200 up to 21FF. All right, that's how much, which gives me 8 kilobytes. Okay, so I can write from here up to here. If you added in some external stuff, then you can go down to here. All right. If you look at it. I added this into this figure yesterday. This just gives you the data memory is always equal to, as Miles was so kind to put it again, it's the I/O registers plus the SRAM plus your general purpose registers. This is table 2.1. Okay, so it breaks it up for the, here you can see for the ATmega 16s, you got 1120, your I/O's got 64. SRAM is 1K. Again, here's my SRAM, which is 1K. And then I add in my 32 general purpose registers, which gives me 1120. The ATmega 32 is slightly larger. Okay, because basically what you have here is you still have the 64 I/O registers, you still have the 32 general purpose registers, but you've got, instead of 1K here now, you've got 2K. So the ATmega 32 gives you 2K of SRAM. The 169P gives you 1K of SRAM. The Mega, if you notice here, has a lot more. I've got the 64 plus these other 416, plus I have 8K. So I have 8K of SRAM to write to, and then if you notice, it's always constant throughout. I have 32 general purpose registers for any one of the Atmel series processors. Okay, you've always got the 32 GPRs that are in there. All right. So let's take that code. We're going to run it on 2560. Oops, I already got that. Oh, I clicked on that. And we pick our simulation tool. Simulate it. All right, let's build it. All right, and let's run it. And let's bring up IRAM. Now you'll notice when I clicked on the IRAM here, where does it start at? 0200, which is for the 2560. Okay? So it defaults. When you go hit IRAM, it defaults to the first memory location for SRAM. Okay? That's just where it goes to, because that's the beginning of it. All right? I'm going to show you a way that you can, we will find this number. There's a way that you can find the beginning of SRAM, and there's a way you can find the end of SRAM. I'll show you how to do that. But for our purposes, let's just step through this guy. It's the internal RAM. It's SRAM. IRAM is SRAM. They're synonymous. Okay? Yeah. It's just the way that Studio 6 has. It's SRAM. What is that? First address of SRAM. Okay? All right, cool. Yeah, it's amazing all the vernacular that you get in microprocessors. I mean, if there's one thing I've learned working for like NASA and the government, acronyms. Acronyms are everything. You've got to learn, like, what's ISP?
Internet service provider.
Internet service provider. There's also another term for it. ISP is on your butterfly board. What's an ISR? Interrupt service routine. All right? What's SQL? Sequential query language. You got to love the acronyms. All right? It's a beautiful thing. All right. All right, so we run this guy down, and then we're just going to go look. Now, again, we can jump around in here. And here, all we did was just, we wrote it. We wrote those two numbers in there, okay? And there they're sitting at 1,000, okay? Now, if we go and we do this, let me just stop this process from going on. Now I'm going to put in here, instead of 1,000, we're going to put in 100. And this is going to answer your question, sir. All right? When we build this guy, now we change, let's go down to IRAM, and we're now going to physically change this to, instead of 1,000, it's going to be 0100. All right, you'll see that the A3 gets written there, and you've got some stuff going on here. A2, B6, A3, all right? You will notice that we're writing into here. You don't see an A3, right? You see an A2 there, all right? Here's what's happening. we are now writing into here. All right, that's where we're writing to. So you got to be real careful when you write into here, because if you notice that it didn't write an A3, it written like an A2. In some of these registers, and these are all 8-bit registers, some of the bits are preset. You physically can't write to it. All right. So we were trying to write into a memory location in here that we're not. You basically can't write to it. Okay. So you just have to be careful about that. Does that make sense, everybody? Okay. Does that answer your question? We're good. All right. Now, if I, let's see. Oh, okay. Let's go back. Let's change this now. Let's stop this process. So stop the debugging. I'm now going to go over, change the device, and I'm going to change it to the 169P. And let's go back, and we're now going to just make this. Let's go back and make this 1,000 again.
Professor,
Yeah, go ahead.
what if you want to write on the special functions register? What would you do?
Hold on. Let me just modify this. If I want to write to a special function register, there's all right, his question is, how do I write to a special function register, right? How do I write to it?
Use in and out instructions, but
I can use in and out,
okay, but
or I can physically, again, if I want to, you can write in here, all right? There's ways to write to, like, let's say I want to write to a timer in here. I want to set a timer to basically time something, all right? You can write to that register. There's certain bits in that register I can physically write to. Matter of fact, if you want to look, if we go down, all right. Give me a second. Yeah, here we go. If you look in the 169P manual, I'm going to show you how to write to port B, just some LEDs. There's a port B data register, okay? And I have to write to it, all right? It's got all these these are all bits on that register. There's also a data direction register, so I can tell each one of the pins, pin 0 through pin 7, I can select each one of them to be an input pin to accept the voltage in, or be an output pin. So this physically has a memory location, and that's the physical memory location of where it is. All right, so if I write to that memory location, I'm setting the data direction register for port B to be whatever I write those 8 bits to be. So that's how I would basically write to a data, I can set DDRB, all right? And now, I think I actually have it in here. Yeah, I'm reading pins. I can have pins as inputs, outputs. Let me grab. Yeah, here. I set the data direction register DDRB equal to, this is all binary, 1 0 0 0 1 1 1 1. What does that do? It sets bit 7 to be a 1, 6, 5, and 4 are zeros, 1 1 1 1. That selects these guys, this to be an output. Pin 6, 5, and 4 are now going to be inputs. 3, 2, 1, and 0 are going to be outputs. So I'm setting those up. And then I set port B equal to, this writes to port B. So I'm now going to write to port B a 1. So if there was an LED sitting on pin number 7 of port B, the LED would turn on. Off, off, off. The LED sitting on pin number 4 would turn on. Pin number 3 would be off. You know what I mean? You get my drift here? All right?
What about pin B? Pin B.
P-in?
P-I-N-B.
Well, what pin B is different. That's in.
So I mean, another register we call pin B.
Yeah.
So what does it stand for?
Oh, we'll get to it. I'm jumping ahead here. What am I on? Slide number 98. You got me. I'm a little bit of. We're getting to it, my man. We're getting to it. All right. All right. So getting back to this guy here, if you run this on the 169P. You will then notice that I'm not writing to memory location 1000. Is on SRAM 1000 for the 169P. What does that mean? Is there such a memory location? You're outside of it. This only goes up to on the 169P 4FF. All right? So now what happens here is it's going to take, since I can only address up to 4FF, I'm no longer have 16-bit addressing going on the 169P. It ignores that, and that. So now I'm writing to memory locations 0, 1, and 10. Okay? And you will see, if you notice, R0 has the A3 in it, R1 has the B6 in it because that's sitting at memory location 0 and the other one's sitting at memory location 1. So I go in here and I just simply go down to where my general purpose registers are at 0 here. I see the A3 and that is sitting there. What's that? It does that. What's that? It's going to be this. It's just not lopping that off. Okay? It just lops that off. Is that okay, everybody? Okay, all right. Let's rock and roll here. All right, so again, the only point I was trying to make with these slides is you got to know where SRAM starts and ends. Okay? You got to know where it starts and ends at. All right, now there's some other examples that I have in here on transferring data back and forth. So I'll just let you can actually look and run it and read it there. All right. All right, again, okay, now, on your lab next week, we're going to be writing to, or we're going to be using the 2560, which allows me to do 16-bit addressing, okay? The question is, how do I generate a 16-bit address? Because if you notice, all of these registers and all this stuff is 8-bit registers. All the general purpose registers are 8-bit. Okay, just wondering. All right. What we can do is we have something called here the X, Y, and Z registers. These registers, I have an XL, which is the lower byte of the X register, is going to be register R26. X8 is going to be register R27, which is the higher order byte of the X register. So these two together and these physical memory locations can form a 16-bit address that's like now I can go and address 16 bits. So these guys down here, I can use them to actually, the X, Y, and Z registers are 16-bit pointers for addressing memory in 16 bits. Okay? So these are referred to as, the X, Y, and Z are referred to as pointers, all right, for addressing data memory. Okay? Now, if you have extended memory, we're not going to worry about this because we're not going to have it. I just thought I would mention it to you. You can actually generate up to a 24-bit address, all right, if you have extended memory, all right. We're not going to worry about that. It's called the ramp X, ramp Y, and ramp Z. Don't worry about this. We're only going to be working with these 16-bit registers here, okay? All right. So now, let's say I want to transfer R17 and R18 to a memory location that's sitting at 1002, 1003, and then move them into R0 and R1, all right? So here I'm going to load up R17 just with a number. I'm going to store that number at this memory location, the 16-bit memory location here, all right? And then what I'm going to do is I'm going to load into R26 the lower order byte of this memory location. I'm going to load into R27 the higher order byte of that memory location. And then I'm just going to do an LD, which is a load. This 16-bit address, which is in the X register, which is comprised of R26 and R27, and it's going to load that into R0, okay? So that if you run this code, if you run this code, you will see that we're going to take, here's my, I'm loading this guy in, A3 into here, R17 then gets loaded into that memory location. We're then going to take this 16 bits and store it into XL and XH. Then I'm going to take that contents, this is the contents. So this is like an indirect addressing. It takes the X register, the contents of the X register, and loads that into, in this case, R0. All right? And that's where you'll see the R0 now has the A3 sitting in it. Okay? All right. Let's see. Write an instruction sequence to swap the contents of data memory location 2000 and 2001. Now again, as soon as you see this, you know you can't be running on the 169p or the Atmega 32. You have to be running it on a 2560. All right? Because you physically don't have these SRAM memory locations. So here we're going to load up. I need some data, so I'm going to load a 3 into R17, and I'm just going to load that R17 into 2000. I'm going to load a BA into R17 and move that into 2001. All right, now I set up the address. The lower part of the Y register, load immediately into the lower part of the Y register, 00, which corresponds to those two, that low order byte there. Then I'm going to load into the higher part of the Y register, the higher order byte of that 16-bit address. Then simply what we do is we load, that gets loaded into R0. So what is in R0, it's going to be basically the contents of 03. Then what we do is we do a load with a displacement up to, now what this does is this increments Y, so now it's not going to be 2000, it's going to be 2001, and then that gets loaded into R1. All right, and then we're simply going to we're going to perform a swap. We're going to take the contents of R1 is going to get loaded into Y. The contents of R0 is going to go into Y plus 1, and then it simply does a swap for you. Okay. How we doing? 3 minutes. Okay. All right. All right. So that's just using the X, Y, and you can use the Z registers to generate 16-bit addresses for you. Okay? Everybody all right with that? So on your lab next week, you'll have some examples of basically that. All right. In this data address space, we got RAM. We're now going to look at some of these ports over here. All right? We're going to look at some of the I.O. pins. I don't know why this came up real light, but I'll have to try to fix this. You have what's called an in command. Sorry, it's really light, but in, RD, and an I.O. address. What this does, if I have, like on your butterfly board, if port B has some inputs to it, if you had like a little voltage and then some dip switches, you can actually set them to be inputs. So I can read in data coming in. You can think of it as like being like door alarms or something. I mean, they're all just going to be attached to a set of I/O pins on an I/O port. And then the in command basically is I just take a register that's going to accept the 8 bits in, and then I just give it the address of where that register is. All right. I can also write out to an I/O port. So if I need to physically write out to this I/O port, I can go out, give it the port address, and then give the register contents. If I'm going to write out to it, I need some data to write out to it. It could be the contents of a register. All right. So for example, if I do an out to 3F R12, 3F happens to be the location of my status register. So I'm going to basically put the contents of R12 is going to go into the status register. Or I can have the outputs of R15 going into 3E. 3E happens to be the memory location of the stack pointer high. All right, so I can write to there. I can do outs to R12 to the stack pointer high. I can go in. I could take the contents of the status register and bring it in. Now, if I want to write a program that adds the contents of P in C, all right, so I'm going to take the port C register to the contents of P and D and store the result in memory location 090. So here all I do is I now read in pin C, which is going to give me the contents of port C. It's going to get loaded into R20. D gets loaded into R21, add them, and then store them. Have a good weekend.